Exam review, everybody would be okay with that?
Yes.
Wednesday, Thursday. Let me think about that. We'll discuss on Monday. Diels-Alder notebook pages. Those do on Tuesday. Test is on Wednesday.
Yes.
Yeah. Diels-Alder page is due in class on Tuesday for both labs. Any questions about mass spec? Including the blue handout, the GC mass spec of the group lab product? Any questions about that? Are we ready to look at some mass spec? Or should we look at it on Monday?
I wanted to watch it every weekend.
Asia? Okay.
There's not like just an easy way to know exactly what's going to break there, other than if it's how it's international.
I'm looking for the best cation typically. Where's the best place to form cation? And then you would break it there. Lose something there to make a cation. Problems in the workbook. Example type of problems, same type of problem you'll see on the test in the workbook.
Is it going to be like how the IR was, like the last page is like 2 or 3?
Just like in the workbook. Okay, substitution. Let's see where we're at. Williamson ether synthesis. Amines. Amines can be directly alkylated. We have a sp3 nitrogen. We can put an alkyl group on that sp3 nitrogen. That's what we did here. But we need to include a base because at this point, to go neutral, you got to remove a proton. And Br minus will not remove proton. Whatever the leaving group is will not remove the proton. You got to include another base. We have possible for polyalkylation. Through this scenario, ammonia can act as a base in the reaction. If you have ammonia in the reaction, as soon as one molecule of this is formed, ammonia can remove the proton. Free that up, now this can react again, and that's how you can end up with 2 alkyl groups on it. If we look on the very back, you're going from 42 to 43. What are they doing? The bromine, the leaving group, is being replaced by this nitrogen here. Now it's actually 2 steps. The second step, they're removing this ester group from this other nitrogen. Don't worry about the second step. If they didn't do the second step, this would still be here. What's going on here? This nitrogen is being alkylated. Here it has 2 alkyl groups. Now it has 3. 1, 2, 3. All right? What's the purpose of the base? By the way, they're using xylene. They don't say which isomer. Orthoxylene, metaxylene, paraxylene. Have you ever used xylene as a solvent? Reflux. How long is your reflux with xylene? What about 10 hours? We'll be doing that lab on Thursday, Friday. That's nothing. You can reflux for overnight. Very common. 24 hours. Okay, forget about the second. First, here. This nitrogen is replacing the bromine. Purpose of the base? Because you're going to produce HBr, just like on the previous page. You've got to remove the H from this nitrogen. You've got to remove that H. The bromine is not going to remove it, the bromide. Include a base, such as carbonate, to remove the proton. That's how we get a neutral product. Okay? What's the mechanism for this reaction? I say SN2 most likely. Does that make sense? SN2? Could this be SN1? Why could it be SN1? Carbocation. Could you make secondary cations? Yeah. Not only would it be secondary, it would be also what? Yes, it would be resonance stabilized by 2 different benzene rings. Yes. Maybe it is SN1. I said SN2 most likely. Well, how do we know? How would you determine the mechanism, SN1 or SN2?
Increase the amount of the
Yeah, you would change the amounts of the reactant.
Change it. Okay, which one? What would you change?
Any of them, right?
I wouldn't change any of them because
you change the amount.
some of them are involved in both rate determining steps.
Would it be reagents?
Which reactant is not involved in the rate determining step of one of the mechanisms?
It's the one that doesn't have the thing that comes in the back.
SN1, the nucleophile is not involved in the rate determining step, so we can change the concentration of the nucleophile. What if we change the concentration of this? What if we double the concentration of this and the rate is doubled? What does that tell us the mechanism is?
SN2.
Tells us the mechanism of SN2. What if we double the concentration of this and the rate doesn't change at all?
SN1.
Sounds like it's SN1. We can also possibly do stereochemistry. This is a carbon, but it's shown generic. But if that was R, and this ended up being S, what would the mechanism thus be? That would tell you that the mechanism must have been SN2, because you've got inversion. What if you started with R and your product was a racemic mixture? Tells you it was SN1, because SN1s give racemic mixtures. SN2 gives not. SN2 gives inversion. Okay? There are ways to determine your mechanism. There are other SN2s here. There's actually 3 SN2 reactions. Right here. What's going on here? This nitrogen is kicking off the chlorine. SN1 or SN2? Chlorine's now gone. Nitrogen's there. Mechanism. Vernak? Why?
Tertiary carbon? Not tertiary, tetrahedral carbon. Takes it off.
Yeah, but by what mechanism?
Because it's a strong anion.
What's a strong anion? I don't see any anions.
Once the chlorine leaves, won't that whole thing be negative?
Each one of those carbons is a primary carbon. You don't make cation on primary carbon.
Exactly, you don't make cation on primary carbons. I'm not sure what you're getting at. What do you mean, anions?
Never mind. Yeah, I didn't think about that.
Well, what were you thinking about?
So I was thinking about how, like, whenever you determine, look and see if it's an SN1 or SN2, you see if the, once it ionizes, if it's going to be a strong base or not.
No, you're looking at the nucleophile. Is it a strong or weak nucleophile? Leaving group is never going to be a strong base. Okay, there are a variety of SN2 reactions there. Take a look at it. Okay, there are alternatives to direct alkylations. Let's look at one here. We can make the same product shown on the previous page, but in better yield this way. Not by just taking ammonia and kicking off a leaving group. That would be a direct alkylation. Here's an alternative. Instead of ammonia, you can use azide. NaN3, that's azide. What's the charge of the N3? That's right, minus, because sodium is plus. Lewis structure for N3. You did a Lewis structure for that back during test 1. It was in the workbook, I believe, asking for Lewis structure of azide, yeah? Azide Lewis structure. Like this, going to have 3 charges. Net charges minus. One of the nitrogens, either one, these electrons come in here, kick off the leaving group, and that gives you this here, alkyl azide. Right, Lewis structure is now, how many lone pairs left on this N nitrogen? 1. Everything else is the same. That's a plus. That's a minus. This is now neutral. So the whole thing is neutral. There's 2 carbons and then the N3 neutral. That's it, just condense. At this point, a reaction you can do is react this with hydrogen and a platinum or a precious metal catalyst. It will cleave off 2 of the nitrogens, put 2 H's on the 1 nitrogen remaining, and you get the primary amine. Okay? Instead of using ammonia, ammonia would be a direct alkylation, putting 1 alkyl group on ammonia. Instead using azide. This gives a better yield because you don't have trouble or problems with polyalkylation. Once this alkylates once, it's not going to alkylate again. Even this end will not alkylate because it's so withdrawing here. It does not alkylate again. Alternative approach to direct alkylation. We can call this an NH3. It served the role of NH3. We replaced NH3 with this. Got the same outcome, but the azide did it instead. What can we call this? This term is used in pregnancy if somebody else carries the child.
Surrogate.
Yes, this is an ammonia surrogate. It did the job of ammonia. But it did a better job because it doesn't do polyalkylation. We also just get to see another nucleophile doing an SN2 reaction, azide. Right? Synthesis of quaternary amine salts, also known as quats. If you take this tertiary amine, you can get a reaction here. It's not easy, it's going to require heat. This can come in here and kick this off, SN2. What would that give? It would give this product here. The nitrogen is now bonded to an ethyl group. Nitrogen is now positive. Then the leaving group sits here, B or minus. This nitrogen does not have a proton. It's not going to easily go neutral, even if we included a base. Well, I'll take that back. If you included a base, you might get some other chemistry going on. But you can just stop here. Just like on the previous page, you could just stop right here. If you don't include a base, this will be your product. Unless you get polyalkylation going on. It would just be the salt. Only if you include a base does it go neutral. Well, it's the same thing over here. If you do not include a base, it's just going to stay like that. But again, even if you did include a base, there's no proton here to take and leave the lone pair behind. But this nitrogen is now bonded to 4 alkyl groups. That's tertiary. What do you call this?
Quaternary.
Quaternary. It's a quaternary ammonium salt. The positive nitrogen is called an ammonium. And a lot of times for nitrogens, quaternary is shortened to just quat. You could also do that for a quaternary carbon, but it's more common when you hear quat, it's referring to quaternary nitrogen. Okay? Why is this going to be a little slow? Why does it need heat to help it?
The nitrogen is not going to want to become positive.
That's not the reason, because nitrogen will become positive. I mean, the previous reaction, it'll become positive. It'll react. Why does this need heat compared to some other similar reaction? What's difficult about this reaction? At this point, guys, we've talked about a few things that are critical to these reactions.
It's crowding. It's going to be hard to get in there.
Okay? I'm asking you to just provide the steric crowding. It's crowded, right? It's a tertiary amine. Crowding around here. We talked about that. I actually call triethylamine a non-nucleophilic base. Well, that's kind of relative. It's non-nucleophilic compared to a better or non-nucleophilic nucleophile, or non-nucleophilic. Everything's relative. That's compared to a better nucleophile. We didn't say it's absolutely never a nucleophile. That's a tertiary amine acting as a nucleophile. It's probably a little difficult, probably requires a little heat. It can be done. Quats can be made this way. Okay? What are quats good for?
One time I asked that and someone said absolutely nothing. And ever since I always wait for that. I never get that response.
What are quats good for? Well, you'll see quats along the way if you keep your eyes open. Choline, you ever heard of it? Maybe not heard of choline. Have you ever heard of acetylcholine? Some people say acetylcholine. What's acetylcholine? Thought you heard of it. Okay. Acetylcholine, neurotransmitter. You'll see in biology and biochemistry, etc. It's choline with an acetyl group added. Okay? But here's choline. And what do you see in the structure?
Quite.
A quad, right here. Okay? How about over here? I know this compound. It's a quad. What's on the quad? What is that group? 10 carbons. Decyl. Didecyl. Dimethyl. Ammonium. Positive nitrogen. Chloride. It's a common topical antibacterial. Ever go over to the Y over on Wheeler Road area? They got on the walls these little things, and you get this. Look at the label on it. It says that right there. That's why I put it there, because I was over there one day. I'm like, I'll put that on my handout. All right? These types of quads are used because they disrupt the, you biology students know better than me, they disrupt the cell membranes or something, kill the bacteria. All right?
Yeah, we learned, Bates taught us that it was useless to put those in hand sanitizers though, because hand sanitizer is always antibacterial anyway, and that just leads to resistance.
Why are they antibacterial anyway?
The alcohol kills them.
Well, I mean, certainly, your little hand things you buy at Walmart for 9 cents on the way out, mainly alcohol. Yeah, but some of them don't have alcohol. I don't know what you were told, but
It was Bates.
How about this one down here? What is this? It's a quat. What's the anion? Not a halide, but it's this benzoate, organic anion. But it's a salt, right? Plus and minus, ion pair. All right. What's it? It's called denatonium benzoate. It's known as the world's most bitter compound. It's put in things like antifreeze, to keep little kitties from drinking it. Because antifreeze is otherwise a little sweet, and cats will drink it. It's good, isn't it? And I think we had a cat one time because there was some antifreeze sitting around right after the cat I found him dead. Or people poison cats like this. They drink it up because it's a little sweet tasting. But in some places, particularly like in Europe, they put such compounds in it, and then the cat goes, won't drink it. It's like, ugh. Okay?
So we don't add that to ours here.
I'm not sure, but I think I saw it done in England or something. But there's other things that you might not want kids or animals to drink. So putting something bitter in it, I'm not drinking that. Good, because it's toxic. All right? World's most bitter compound. It's a quad. What else is there? I see an anion. That's the anion of a carboxylic acid. Okay? Beautiful compound, yeah? It's a salt. Ion pair.
Okay, alkylation of carbanions. What have we done before? We've been looking at nucleophiles. We looked at oxygen. We just got through looking at nitrogen. What about carbon? Can carbon be a nucleophile? Substitution reactions require the nucleophile to have a lone pair. This has a pi bond. It can react as a nucleophile in certain reactions. The pi bonds typically are not going to do SN1, SN2. You need a lone pair to do SN1, SN2. Has no lone pair. Not a good nucleophile for SN1, SN2. Can we create a lone pair?
Yes.
Yes. Lone pair on a terminal alkyne carbon. We talked about this. This was the last thing we covered for test 2. We said that we'd be talking about it during test 3. Test 2, we made these anions. I said during test 3 we will react them. Well, now we're doing it. First off, what base would make the anion here? In-butyl lithium would work. There was another one I told you. The other one is actually more classical textbook. The other one was included on the test at the bottom. I got test 2, last question at the bottom, first page. First page.
Oh, the things with the D.
The D.
Yeah, the D.
Yes, because once you make the anion, you could react this with a proton source, or deuterium, same thing, and you can put the proton back on, right? You come back this way with some type of proton source like water, it'll take the H and go back. But if these are Ds, you'll have a D there. What base did we use? Yes. NaNH2. That's a common base used to do this. That's more textbook. In practice, something like in-butyl lithium is better. In practice, that's a lousy base. I don't know why textbooks like it so much. Lousy base. Problem is it ain't soluble in any organic solvent because it has no organic nature to it. And you can't put it in water. If you put it in water, it's just going to convert to hydroxide. Lousy base in practice, textbooks love it. Better base. But you're not going to hardly ever see this in textbooks. I don't know. But once we make the anion, now we have a good nucleophile. And these electrons, we throw in a carbon with a leaving group. What's the leaving group here? Tosylate. These electrons attack here, kick off the tosylate. What's the product going to look like? That's just a phenyl. That product there. Good old SN2. Does that product look right?
Shouldn't that be going back?
Yeah.
Shouldn't that?
SN2, SN2 comes with inversion. Just like Big Mac comes with fries. SN2 comes with inversion, right? So it's very important. But I did show inversion.
Yeah, because the methyls going down.
I did show inversion. Right?
Yep.
I mean, here the ethyl and the D were over here. The ethyl and the D is down in like this, right? The group comes in, what do these do? They straighten up the planar. And then when the leaving group leaves, they come this way. It's inverted. Do not fall in the trap of inversion has to go from bold to dashed or dashed to bold. Not always. Just like this. Here we go. Here's a right hand with the thumb that way.
right? Now, when I switch and show you my left hand, do you expect the thumb have to go this way? Not going that way, correct? But guess what? Here, okay, pay attention. I'm going to switch hands. Here we go. Right hand, thumb facing that way. Now I'm showing you a left hand. The thumb's facing the same way. Right? I mean, I can show the product any way you want. It does not have to be. That is inverted. We can also do RS if you'd like. Here, what is RS? Oxygen 1, carbon's 2, D is 3, H is also here, but it's going back. So what is this? S. What is this here? Carbon or carbon? Well, this carbon is bonded to 3 carbons. That one's only bonded to 1. So this is 1. That's 2. D is 3. H is going back. What is this? R. Again, do not fall in the trap of, if it's bold, I have to draw dashed. It all depends on how you draw the backbone. I could have drawn this the same exact way. I could draw this same compound with that dashed. I'd have to just flip it around. Okay? Careful, don't fall into that trap.
So if you left stuff, like everything kind of drawn in the same position, but you did it dashed instead of bold, that would also be correct.
Yeah, can you show what the dashed product would look like?
Well, if you just flip this around, see right now the ethyl's coming forward. Correct? Ethyl's coming forward. If I just do that, now it's going away from us. I mean, I could show it, the D here, put the alkyne over here, and put the ethyl like that. This is also R. That's the same thing.
The mirror image.
No, these are not mirror images. These are the same thing. I just turned it around, just like I just did that with my hand. Same hand, right? Right? It's still R, isn't it? This is 1, that's 2, that's 3. Uh-oh, it's counterclockwise. But the H is now coming forward. So you reverse that to R, and you see that R is R. It's the same thing. We'll do more of these. We'll do more of these. Yes, it's possible to keep the backbone the same or something. But I did it like this because this is really more in the inversion. Because the nucleophile is coming in over here, right? Here are the 2 groups. Nucleophile comes in. What does it do to the 2 groups? It straightens it up with planar. And then when the leaving group over here leaves, these 2 groups, they move this way to make room. This ethyl is forward. Correct? It's forward, and it's also that way. But then it goes planar, still forward. But then it comes this way, still forward. That's all inversion. All right? It's all there. Again, whatever works for you, but that's the inversion. Cyanide. Okay, we used a carbanion here. Carbanions can be nucleophiles. Cyanide. Well, this is KCN, right? If you look at cyanide, the carbon is a carbanion. Now, something like potassium cyanide you would just buy. That's a small reagent that you would just buy. You would never have to make that. Not these days. Just like sodium hydroxide, you would never have to make that. You just buy it. Sodium chloride. No, nobody's making that. Well, actually, somebody is, but that's a huge company or something that makes that bulk. Or they get it out of the ocean or something. But any lab is just going to buy sodium chloride.
by this. See, this you're going to have to make. It's a specialized, from this. It's by that, but look, it's a carbanion. Good nucleophile. These electrons come in here, kick that off. Let's show stereochemistry again. I would do this one. Now this one's going to look more like what was kind of mentioned. I'll draw this as a benzene ring, I reckon. Boom, boom. And put the cyanide. We can just keep that as CN. Unless you were asked to draw a formal, full Lewis structure. Nitriles are typically just showed CN. But you know it's a triple bond between the C and the N, and the nitrogen has one lone pair, right? And so that was dashed, and yes, I would show that one bolded. Because if you keep the backbone the same, your inversion, because look, the leaving group is back, so how does the nucleophile come in?
Forward.
From the front. That's more straightforward. What's the difference? The difference, which none of you probably recognized, is here the leaving group is forward or back. What was it up here? It was in the plane up there. Since it was in the plane, how does the nucleophile come in? Forward or back?
In the plane.
In the plane. So that's why, in the product I showed, where's my nucleophile? I mean, the nucleophile in the product, how is it projected? In the first structure I drew, the first product I drew.
Plane.
In the plane. Because the leaving group was in the plane. But down here, the one at the bottom is more sort of conventional, straightforward textbook. But you should be able to deal with the one at the top as well. Because if it's in the plane to the right, how does the nucleophile come in?
In the plane to the left.
From the left. Well, that's backside. All we do is just turn it this way. If the leaving group is forward, how does the nucleophile come in?
Back.
Opposite. Here it's going to be back compared to your view. Okay? Hey, what is Dmso?
The stuff you rub on your skin.
Can be. Or horses. It's a solvent, common solvent, not that toxic. Because sometimes people rub it on the skin, and it's a horse liniment. Dimethyl sulfoxide. It's a very polar solvent. It was on the list I gave you, handout back week 1. Polar solvent. Got to get used to seeing solvents, recognizing them. Solvents, by definition, pretty much don't react. So we just ignore it. Okay, proving mechanism by Regio chemistry. Let's look at this mechanism. If you take this compound and heat it with ethanol, we can get a reaction. And I'm showing Regio isomers, 2 different constitutional isomers. And I'm showing HBr being formed. That's the fate of one of the H's in the leaving group. Now, ethanol is kind of like a solvent. And here the solvent is reacting. That's why it's called a solvolysis reaction. If your solvent does react, we say call it a solvolysis reaction. So this is just like heating it in a solvent, almost. But the solvent reacts. Mechanism here. Is it a substitution reaction? Just look at just one product. Is it a substitution reaction? Yes. Something's replacing the bromine. What is replacing it? This guy. The oxygen.
But this is losing an H. It has to lose an H to go back to neutral. It's a substitution reaction. Is it SN1 or SN2?
That's a two.
Because it's not a strong,
What does SN2 require?
strong.
I think we had some exclamation points with this on the previous page. SN2 requires what?
Strong.
Strong nucleophile, yes. Because the nucleophile is involved in the rate determining step, the hard step. Nucleophile has to be strong to do that. Is the nucleophile strong here?
No.
What is the nucleophile?
Weak.
Ethanol, and it's,
Weak.
I know it's weak.
Because it doesn't,
Is it an anion? Is it sp3 nitrogen?
No.
Then it's weak. Mechanism. SN1, we can tell that already. We can also tell it's SN1 because of your Regio isomers. Okay, show the mechanism. What's the first step of the mechanism? What's going to be the first step? With a little heat. See, this is not strong enough. That's not strong enough to come in here and kick off the leaving group. Only thing can happen is the leaving group
Weak.
just leaves. Can it just leave?
Yeah.
Yes. Yes. What happens if you put HBr into water?
They leave each other.
The bromine leaves and it becomes what? H plus and what? Br minus. Can the bromine just leave? Yes, it's called ionization. Just leaves an H. Now usually something is coming in here with the H, because H plus doesn't exist by itself. But C plus does. That just leaves, and what do we get? Boom, boom, boom. Boom, boom. Carbocation. How do you get the first product? Now the nucleophile. See, nucleophile is weak. I'm going to say it won't get off the sofa. It just wants to sit there. I can't do anything. I'm too lazy. I can't kick it off. You're just going to have to do this yourself. But now the nucleophile will add here. Now we got a much easier reaction, reacting with this full plus. See, that was only partial plus. Too weak to attack that. But it will attack this. These electrons here, what does that give? Oxygen here. There's an alpha group on the, we want to draw this out. Alpha group, and an H, and one lone pair, and that's a positive charge. We don't just magically lose H's. But from here, how can we get this product here?
Your BR comes in and takes the H.
We do have a Br minus floating around. These electrons can take the H, these stay behind, and we get that plus what? Plus HBr. But how do you get the other product, the second organic product? What are carbocations prone to doing? Rearranging. How do you expect this to rearrange? There's an H here. These electrons will break away and move over here. That gives boom, up, boom, boom, boom. Cation there. Do I need to draw in the new H? Everybody knows there's a new H here now? There's one there. There's two here. from structure. Neutral carbon with 2 H's. We went from secondary cation to tertiary carbocation. Now do you see how we get the other product? Now the ethanol attacks here. We get a product, you can show this. Then we get home. Okay, I'm not going to do the last 2 steps. It's the same as the 2 steps before. You've got to take care of the proton. Which product do you think is major? You're asked, which of the 2 products is major product? We said this before. Anytime you can rearrange, that's going to be the major root. How would you get any of this? Maybe the ethanol attacks here before it rearranges. All depends on how fast it rearranges. Are these resonance structures?
Yeah.
No, because one of the golden rules of resonance is you never move any atoms. And you only move pi electrons. What type of electrons did we just move there in our mechanism?
Sigma.
Sigma bonds. These are not resonance structures. These are 2 different cations. Each with different stabilities. The fact that we got regioisomers shown here tells you it's SN1. Do you expect regioisomers for SN2? If it was SN2, the nucleophile would be bonded where? Right here, because nucleophile would come in and kick the ligand group off. Right there. SN2 doesn't give regioisomers like this. This reaction screams SN1 for a variety of reasons. One of the main reasons is weak nucleophile. Can you do SN1 here? We didn't make a primary cation, did we? No, we made secondary and then it went to tertiary. So we didn't make some ugly cation. All right? What would be the stereochemistry if we did this with stereochemistry? Same exact reaction, but now I'm showing some precise stereochemistry. Show each product. What would the stereochemistry be of each product? Same products, but what would be the stereochemistry? How about the first product? Redraw it with stereochemistry. That carbon of the product would be racemic. And this would be the same. Nothing happened over here. What do I mean by racemic? You would actually have 2 different products. One of them would be bolded and whatever, bold something over here. The other would be bolded and reverse that over there. This is always going to be bolded. Never did any chemistry over here. You'll draw a product with this being R and with that being S. This will never change. That's what I mean there. What would the other product look like? Look like that, right? I didn't imply anything with darkening the leading line. This is. Boom, boom. That's it. But I thought I was supposed to show stereochemistry. There is no stereochemistry in this product. There's no chiral carbon. Is that chiral? That? No. Yes, it's tetrahedral, and one is forward and one is back. Draw it however you want. There's only one way to draw it. There's not two compounds anywhere. So the other product really doesn't have any stereochemistry. Right? But this one does. It's got 2 chiral carbons and has 0 chiral carbons. Okay, what's the rate equation for the above solvolysis reaction? Rate equals what? Some type of constant times what? Alkyl bromide times what? That's it. SN1. Does it matter how much ethanol we use? If we use more ethanol, is that going to make the reaction faster?
No.
But if there's more ethanol, there's going to be more chance of attacking the cation, and it should be faster, right?
Doesn't matter if the leading group.
That doesn't matter. Yes, the fast step may be faster, but does that change the overall rate? No. You can make the fast step faster and faster and faster, but guess what? You ain't changing the overall rate, right? There's your rate equation. What type of nucleophiles react strictly by SN1?
Weak.
Yes, weak. Weak. Lazy. Because if they were strong, what would it be doing?
SN2.
See, if this was strong, it'd be like, here I come, kicking you off. Strong nucleophiles don't give the leaving group time to ionize. They're bullies. Boom, you're gone. I'm strong, I just kicked you off. Because ionization does take a little time. It's not the easiest thing to do. See, this does nothing. So all this can do is ionize and make cation. Okay, summing it all up, here we go. This should be a summary. Substrates with leaving group on primary carbon only undergo SN2. Does that make sense?
Yep.
You never do SN1 there, right? Substrates with leaving group on tertiary carbon only do SN1. You don't do SN2 with leaving groups on tertiary carbon. I think we had 3 exclamation points for that. Substrates with leaving group on secondary carbon can undergo either. With strong nucleophiles, reaction will always be bimolecular. Either SN2, or on the next handout we'll see E2. But both of those are bimolecular. With weak nucleophiles, which are lazy, reaction will be unimolecular. As long as the substrate is secondary or tertiary. If the substrate is primary, the reaction will have to be bimolecular. Because you don't make primary cations. Of course, a bimolecular reaction with a weak nucleophile will be quite difficult. We could have a reaction where you're like, this test doesn't look like it's good. And you may be right. And such a reaction is not going to happen that easily or at all for various reasons. four at the top. Work on these while we take a 2-minute break. Which one?
Kind of like a kid infection, it's because we stay in school not having any.
You just have to pull the door shut because it wants to hang up. You put your hand on the top and then yank it so that you can
I
lock
give
it.
up, I'm just kind of like stupid.
Stereochemistry doesn't look right on the first one.
There is one version, and this is one version. It's still the same.
No, it's still the same.
Well, carbon is
No, the stereochemistry is not right. This is good. Right.
5D. This one is the because it goes more conversion.
How do you take the how do you take this for Okay, anybody got the product? First one, what type of mechanism are we doing here?
That's the one.
First off, this is substitution handout. We haven't done elimination yet. Once we do elimination, you're going to have to think about that as well. Okay? What type of substitution mechanism is going to happen here? Besa? Why SN1? Yes, weak nucleophile. So what's the mechanism? First step? Leaving group leaves. We get carbocation. And then water attacks it. The weak nucleophile will then attack the cation. All right, get off the sofa and do something now. This attacks. I'm not going to show full mechanism, but product's going to be what? We're now going to have an OH here. After it loses the H, what's going to be the stereochemistry? Racemic. Yeah? Half the molecules will be R, half the molecules will be S. Because how do you attack a carbocation?
From the front.
Front or back? 50-50 chance. How about the one on the right?
Yeah.
It's the same product. The nucleophile here is a neutral oxygen. Over here it's an anion mechanism. This is a bully. Strong. Here I come. Bam, kick you off. You don't even have time to ionize. Product will be what? R only. Inversion. SN2 comes with inversion. Same starting material, two different nucleophiles. Both products are alcohols. This is just a neutral version of the nucleophile. This is the anion version of the nucleophile. Over here, weak nucleophile. Product? Racemic. Oxygen bonded here, we lose an H. You want to balance these up here? What else would be formed here in this reaction? HI? What's formed up here? HBr. What's over here? KBr. Two ions. Bottom right.
SN1,
Why SN1?
because it's a tertiary,
Yes, but what type of nucleophile do we have?
a strong.
Strong nucleophile, right? Strong nucleophiles are bullies. The summary said always bimolecular. SN1's not bimolecular. Bully, here I come. Gonna kick you off. Can it be SN2 though? Never do SN2 on tertiary halide or tertiary tosylate or anything, okay? So what is it? Neither. There will be a reaction though. The reaction is E2. Bimolecular. Strong nucleophile / base. Elimination requires bases. We'll call it a base when we do elimination. This takes us into the next handout, elimination. Please be working the ones below. I'll send out a key to that. It includes kind of a challenge mechanism over here. Quinine. Ever heard of quinine? What was quinine? It's one of the original antimalarial drugs. It's a natural product. If you react quinine with sulfuric acid, you can get a new product called quinotoxin. Try that mechanism. It's a wee bit challenging, but very, very doable. Just got to see what's going on there. Very doable. Louis Pasteur did that reaction. You know Louis?
Yeah.
You're talking about Louis Pasteur in biology classes? You know, Louis Pasteur was also a chemist. Did lots with power compounds, optical activity. Did that reaction right there. He's the first one to document it. heard of Michael Faraday?
Yeah, Faraday cage,
What type of class do you hear from Michael Faraday?
physics.
Well, next time you hear of Michael Faraday in physics, make sure you tell the professor that Faraday was also a chemist. For example, Michael Faraday discovered benzene, isolated from well oil by distillation. The anniversary of that, reporting that, is June 16th. Tomorrow. June 16th, like 1825 or something, 1826, he reported that at a meeting. New compound that was come from well oil.
You mean like the fish?
Yes, they used to take the well fat and heat it up, and it would give off gases and liquids, and they would take that stuff and they would burn it in the lamps.
Wait, are you saying whale?
Yeah, that's
Like
a
a
whale.
well, like a humpback well.
I thought you were talking about like a well, like a water well. I was
Yeah.
like,
Like a humpback well. The blubber. That's why welling was so big in the 1800s, 1700s. They used the blubber for fuel. You take well fat and heat it up in a contained area, and it would just give off this gas. They put it in vessels, and then they would burn it, like you burn gas in your grill or something. Ingenuity, you know, they didn't know how to make it back then. They knew how to obtain it, though, from natural sources. And then Faraday came along and he messed around and got some liquid out of it. Fascinating story. I've got a paper, it's some of his own writings. He talks about how he's trying to distill it and trying to collect a fraction with a good sharp range. Okay, give those a try. Also methamphetamine. Do a little synthesis of meth up there. Okay? All right?
oh, I'm good at that.
I mean,
Also questions on the very front page. Yeah? Okay, next handout is on elimination. And it's our last main handout before the test. There's another topic, sometimes I do for the test, sometimes I do after the test. I decide. It's a more minor handout, last major handout before the test here. Elimination reactions.
before the final or after the third test? Before the final or before the third test? Or like notes?
I'm not sure what your question is.
Well, whenever you were saying like is the last paper one before the test, do you mean like the final test or the test 3?
Test.
Okay.
Test. Not the exam, not the final exam. Okay, there's an example elimination reaction shown here in the synthesis of Tamiflu. Right here. What's going on? What is an elimination reaction? We're eliminating something. Not replacing, not doing a substitution, but eliminating. That's the opposite of what? Yes, elimination reactions are actually the opposite of addition reactions. And guess what? We do addition reactions with alkenes. Well, elimination reactions often form alkenes. This is how you make alkenes. Okay? Why is it covered here, though? It's covered here, though, because it's largely leaving group chemistry. Okay? We'll also have leaving groups. Same ideas. And the mechanisms have some consistency with SN1, SN2. Two mechanisms for elimination. They're called E1 and E2. Right here is an E2. It's an elimination bimolecular. What are we eliminating? When we go from here to here, what's been removed in the formula? An iodine and an H. There's also an H
here that's removed. There's 2 here, there's only 1 there. We're removing HI. And a lot of times you can write what has been removed. We eliminate HI going from 63 to 64. Nothing's been added. Nothing's been removed. You can look back at that. DBU is a nitrogen base. Okay? Beta elimination at what type of carbon? All right, let's find the similarities to previous stuff. General line reaction. Tetrahedral carbon with a leaving group. Sound familiar? But instead of doing a substitution, we can do an elimination. We can remove the leaving group and the hydrogen. And where's the hydrogen located compared to where the leaving group is? It is 1, 2. But we use a little bit different terminology here. Because the first carbon can also be called the alpha carbon. The second one, yeah, the H is on the beta carbon. Because of that, it's often called beta elimination, referring to where the H is. Just terminology. Okay? So when you're out tomorrow night and someone says, hey, did you do any beta elimination this week? You say, yeah, we did some beta elimination. Yeah. Right?
Right.
What do we get if we remove an H into X? We're going to end up with a new bond here. The X is going to leave. It will leave that like a leaving group. It will take the lone pair with it. Okay? But a base is what takes the H. So the base will now have the H. Let's look at a specific example. If we take this alkyl bromide and react it with tert butoxide, tert butyl oxide, tert butoxide, we can get a beta elimination reaction and we can make the alkene. See, we're removing the HBr. It's really the opposite of what? What if we had this 2 weeks ago and we added HBr?
Addition.
What would that give? We'd get such a product like this. Add. Eliminate. We're doing the elimination. We're doing just the opposite. Okay? Yeah? We can eliminate using a base. We get back to the alkene, removing the H and the Br. The leaving group leaves, and the base has taken the H. This now has the H, and it's now neutral. There's a specific. Let's do 2 possible mechanisms for this, just like we did 2 at the beginning of substitution. First one, we're going to do E1. The first step of E1 is the same as the first step of SN1, which is what?
Carbocation.
Forming carbocation. This would just have to leave. What does that give? Carbocation plus what? Br minus. There you go. We've already made one product, Br minus. How you liking this mechanism so far?
Pretty good.
It's terrible for the atom primary.
Exactly. You already don't like this mechanism, right?
Yeah.
I don't either. But we're still going to do it because we're going to do an E1 and show what an E1 looks like. How can we continue on and get those products? We have 2 H's here. I'm going to draw both of them in. At this point, this guy can come in and act as a base. What do bases do?
Take H.
Very good, because on the first day you didn't say they took H's. You said they accepted them. And I said, no, they don't accept anything. They take them, right? They're like a thief. The thief accepted my bicycle. No, the thief took your bicycle. Good, we've come a long way since January. The base takes the H. Bam. Where do you want these two electrons to go if we want to get over there?
This is that positive.
These fall in here like this. The electrons, the nucleus is gone. The H nucleus is gone. The two electrons fall in and make the second bond, and that's the pi bond. What does all this give? We're done now. The base now has the H. We moved in. That is an E1 that I just did. What should be the rate determining step here? Okay, if we drew a reaction coordinate diagram, this, that's slow step. What do you want to call this?
Fast.
Yes. Also, let's make sure we have terminology for what happened. What happened in the first step? Ionization. Ionization of leaving group, right? What happened in the second step?
Beta elimination.
This is actually the beta elimination. The overall can be called beta elimination, but actually removing the beta hydrogen is done here. I'm going to say the beta H removed in fast step. This is E1. Okay, the mechanism for this reaction ain't E1, because you would never make a primary cation. What is the mechanism? It's E2. Well, let's do an E2. By the way, up here, how many? Which of these was involved in the rate determining step up here? Both or only one?
Just one.
Only one. Did that have anything to do with this ionizing? No. That's why it's called E1. See the similarities? E2. Let's show an E2 mechanism. Withdrawing these beta hydrogens. Only one will be abstracted. Okay, how could you do this another way? Same product, but a different mechanism.
Can we do beta elimination first?
What do you mean first? And give what?
Yeah.
Takes hydrogen and then
And form what?
to form conjugate, it forms a conjugate acid and then the electrons bound to the other H would move in, and then that would kick off the braking.
Yeah.
I'm going to go ahead and do it this way. Then we'll do it what maybe you're talking about next. Because there is a third choice on the next page. Yes. Here we go. Now this is concerted here. Let me show you this. What if these electrons do this, these electrons do that, and those electrons do that? That is 3 concerted arrows all at the same time. What does all that give?
The products?
Yes, there you go. That's an E2. How many intermediates in that mechanism?
9.
No intermediates. How many transition states?
1.
1. What does the transition state look like? The OH bond is forming. That CH bond is breaking and electrons are moving in. You see it? And the leaving group is leaving. All that's happening at the same time, one transition state. It's all concerted. There you go. Do you see a carbocation here?
No.
No carbocation. What's the rate determining step?
That.
That one step.
Are they both involved in that one step?
Yeah.
Better be. It's thus bimolecular. We just did elimination bimolecular. E2. Okay? That's the mechanism for the given example reaction. There's a third way we could have showed this. Seems like maybe one or two of you were alluding to this. What if we did it this way? What if these took the H and these just stayed behind like this? Like a good old-fashioned acid-base reaction. Boom, boom, boom. And make anion here. All right, there is one H remaining. I should draw it in since I drew it up here. Plus that, which is, isn't that just a good old acid-base reaction? Did we, and this could be an intermediate, did we show such an intermediate in the previous two? So this is a third way we're doing it. Third possible mechanism. Then how could you go from here to products? Now if we just move these in and kick these out, we'd be home. That gives all that.
Why doesn't that one happen all at once then?
Well, if we did it all at once, I'd be doing the same mechanism as before. I'm just doing it a third way.
But that's not actually gonna happen. I'm not gonna put a negative charge.
This is not the mechanism. This is neither E1 or E2. This has a special name. The only reason I'm doing this is because sometimes you guys try to do this, and this ain't E1 or E2. We never, okay? The first mechanism we showed had a cation intermediate. Second mechanism had no intermediate. This one has a carbanion intermediate, but never this one. Okay, this is the last time we'll ever show this. One thing I can say about this is, in the first two mechanisms, did the leaving group leave in the rate determining step? Look at your previous mechanisms. Yes. Does it leave in the rate determining step here?
No.
What do you think should be the rate determining step? Forming the high energy intermediate should be the rate determining step. LG leaving in fast step. You may look at something like this in organic 2. But not here. This is not E1 or E2. We're never going to make a carbanion. Okay? This last time we'll ever show this. I've started showing it there because some of you try to do it, so I'm really telling you not to. But it's also just exercise seeing the third root. Maybe you could come up with a fourth root. But the two roots we're going to be looking at are the E1 and E2 mechanisms.
You said it has a name, what's the name of
I don't like the name, that's why I don't name it. I try not to remember it. The name is not, it's a little bit confusing to me. Maybe I don't know enough about what they're talking about. It's called an E1CB, with the CB meaning carbanion, carbonated carbanion. I don't quite understand why it's called E1. Because the rate determining step looked like both were involved. And I've never dug into that any further. It's a variation of an E1. We're never going to do it. We did the E1 and E2 like we're going to be doing. Okay. A little note there. Alternative example reaction. If you take this guy and just heat it in this alcohol, or no solvent at all, we can get that plus HBr. As if there's no solvent, what are we saying here? If you just take this guy and heat it,
You can eliminate HBr. It's also called a decomposition reaction because you're decomposing one into two. Elimination, decomposition, both terms work here. Mechanism for this. It's elimination. Is it E1 or E2?
E1.
It's E1. Why? Because E2 requires what? Just like SN2 requires strong nucleophile, E2 requires strong base. There's no strong base here. Weak base. Mechanism. First step. Leaving group goes by. Boom, boom, boom. Cation plus Br minus. We've got H's over here. Rate determining step. This is weak. Or again, no solvent at all. See, the fact that this is weak said it doesn't do anything. It's almost like it's not there. And if it wasn't there, the reaction would still work. Problem is, it might be too dry. Sometimes you need solvent to get things dissolved. And that's why you would use it. Leaving group leap. How can we get home from here?
Br minus takes the H.
Yes, this takes the H. These move in. I'm doing the E1 just like we did before. There you go. We could have used this as a base. Just like if that was water. Water could have taken the H and you would have made H3O plus Br minus. But I'm showing the leaving group taking it, and we can understand how this could work with no solvent at all. Yeah? Okay? That's a good old E1 elimination. Summary statement. Well, we just already did it 1 minute ago. An E2 elimination requires a strong base. Yeah.
Did it ever give us this?
Good question. We'll look at stereochemistry on the next page. Because the alkene is trans. She's asking, what about a cis product? Why did I show trans? Next page. Thermodynamics and entropy of elimination reactions. Let's look at here. Is this reaction driven by entropy? One molecule going to two? Yes. You're eliminating. Elimination reactions are driven by entropy. Is it driven by thermodynamics? Forget about the solvent. What do we went from? What bonds are broken? What type of bonds are broken? Sigma bonds. What type of bond was formed? Pi and sigma. 2 sigma, pi and sigma. Which seems stronger?
2 sigma.
2 sigma. So we're making weaker bonds. So do you think this reaction is exothermic or endothermic?
Endo.
Endothermic. Why do you think I heated it? Well, that's a little bit confusing because heat really refers to activation energy. But usually an endothermic reaction is going to have a little activation energy that's there. Yeah, it's favored by entropy, but it's typically not favored by thermodynamics. All right. Okay. When Regio isomers are possible, look at these 2 reactions. If you do a beta elimination here, leaving group, what type of alkene can you produce? Well, the beta hydrogens are here. I'm just going to draw in one, because we're only going to eliminate one. The double bond has to be between these two carbons, right? That's the only place it can be. But look over here. Here, we could beta eliminate and put pi bond here. HCl, pi bond becomes here. But we could also beta eliminate over here. From here, we got two different beta hydrogens compared to here, the alpha carbon. And if we put double bond in over here, it'd be over there. But look at this. If you put double bond in over here, that's stereogenic. It's trans, but it could also be cis. Is that stereogenic? No. So look at this. That reaction only gives one possible elimination product. Where this reaction gives three theoretically possible elimination products, beta elimination products. Here, we're going to have to decide which is formed. Which alkene will be formed? It depends on a variety of factors. First off, we have some terminology. The most substituted alkene is the thermodynamic product. Why? Because it's most stable. It's called the Zaitsev product. Up here, between the first two, which one's the Zaitsev product?
The second one.
Most substituted, the second one. Well, what would you call this compared to maybe that one? Yeah, both of these are Zaitsev products. By the way, nobody knows how to spell Zaitsev. Spelled with an S here. Some people spell it with a Z. Zaitsev. Because it's really a Russian name. I think Zaitsev worked with Markovnikov. Late 1800s, there were some Russian chemists who were pretty prominent. I typically spell it Zaitsev, but sometimes I don't pay attention. You got two Zaitsev products, stereoisomers of each other. What's the other product called? It says down here, the less substituted alkene is called the Hoffman product. Okay? And Hoffman is one F and two N's. The least substituted alkene. All right, let's end with this straightforward point here. It's written in italics. The Zaitsev product is always a major product in an E1 elimination. Always Zaitsev. But there's two Zaitsev products. We've got to decide which one from there. But not necessarily in an E2. Sometimes the E2 can give the Hoffman. Okay, we'll be picking up here on Monday. But let me ask you a final question. If you wanted the Hoffman product as a product, which mechanism would you have to make sure was the reacting mechanism? A2. Why? Because E1 always gets what? Right. E1 always gets Zaitsev. So if you want Hoffman, you better make sure your mechanism is E2. Everybody agree? All right, let's go home.